All right. Yeah. Thanks for the introduction, Will, and the invitation to Meta. It's great to be back here. I was on the core team when Meta first started pre-COVID back at Stanford with Evan Sherwin kicked it off. So yeah, great to see familiar faces and new faces here. So this is a talk I created at the beginning of the year to highlight how there's through the work that we've done at Highwood, there's different ways to interpret the MII guidance that's out there. So I wanted to show a few simple examples just to illustrate how these differences in interpretation can manifest themselves. Different name I've given to this talk is the switches and dials of measurement-informed inventories. So just to briefly introduce Highwood and the work that we do at Highwood, I'm the R&D director at Highwood Emissions Management, and my job kind of covers a broad swath of the work that we do at Highwood. Highwood's main focus is delivering consulting and software emissions management services for the oil and gas industry. More and more these days, that focuses on helping our clients build measurement-informed inventories for the purposes of voluntary initiatives like the Oil and Gas Methane Partnership, Veritas, MIQ, but also in certain cases, regulatory drivers as well. So from a consulting perspective, that includes a range of things from technology assessment, simulation modeling, and technology deployment planning, but also just supporting clients through the OGMP 2.0 gold standard process. A main focus for myself is on working with our product and development teams on building our standalone SaaS solution, and I'll talk about that more later on in this presentation. So, this is mostly, but not all, an academically inclined audience. So I'm sure many of you could name every paper represented on this slide. I like to use this slide to show, sort of remind ourselves where reconciliation came from. And the idea of reconciliation came from the academic and NGO space, where starting 10 or more years ago, we were using new novel technologies to come up with different ways of estimating methane emissions. Through these studies, which we're calling top-down estimates, we've been comparing these top-down estimates to our bottom-up or regulatory methane inventories and discovering problems with how we've been typically reporting methane emissions. So most of these figures are bar plots, and the bar plots are communicating in these studies mostly, but not always, that our bottom-up inventory estimates are systematically smaller than what we are calculating with these top-down technologies. So these studies have gotten quite a bit of media attention in some cases, and as a result, important stakeholders like investors, the public and regulators are losing trust in how we've been typically reporting our methane emissions, and that is what has motivated the shift towards measurement-informed inventories. So where does that take us from here? So this is what has motivated initiatives like OGMP 2.0, but it's based upon work that I've done here at Highwood and talking to operators. I'd say that although there are specific examples in the literature of reconciling inventories, we haven't exactly figured out how to reconcile or build an MII practically and at scale. What we're seeing on the ground is that there's still a lot of variability in interpretations of this guidance Operators are struggling to scale these things up, and this lack of clarity is a problem for a couple reasons, but mostly like our operators have made commitments now, and we need to figure out a way how to do this. So I have on this slide Ion Methane 2024 from the United Nations Environmental Program. And in this report, they point to some of the issues that have been encountered, or some of the issues that operators have had in reporting at OGMP 2.0. To quote from the report, differences in companies' approaches to reporting the temporal and spatial variability, lack of robust documentation on methods used. In some cases, companies were unable to adequately extrapolate. In other cases, emissions assessments were not properly adjusted to reflect measurement findings. And I don't have a quote from the report, but reporting of uncertainty has also been a problem from what I've heard. So there's technical problems associated with the measurement-informed inventory challenge, but there's also the problems of practicality and understandability. And solving all of these problems is required if we want to report our emissions using measurement-informed inventories at scale. So from my experience working in a consulting capacity directly with operators, I've found that there's this tension between the complexity of the problem and the practical application of the problem. And I'm trying to illustrate this here with these overlapping circles in the Venn diagram. From a business and operations perspective, solutions are needed right now. And from a business and operations perspective, there's this requirement for practicality and understandability, because those that are implementing these solutions need to understand and trust that they're working. Software has a place in this diagram, because software is a way of standardizing a solution and providing this consistency for scalability. And then the academic and research sphere has a place here, because this is still a space that's mostly in its infancy, and it is a complex problem, and there's still a lot of work that remains to be done in order to improve the robustness and the accuracy of our measurement-informed inventories, obviously. And this tension is going to remain for a while, and it's sort of something that we all have to work together on in order to find that center of the Venn diagram, and that's been our focus at Highwood. So before I dive into the details of this presentation, I probably don't need to remind people on this call of these definitions, but I'll just flash them up here briefly. When I say referring to source level or site level, I'm referring to measurements. When I'm referring to top down or bottom up, I'm referring to the inventories. And variance is a word that we have started using at Highwood. We're borrowing it from the accounting space. And variance is what we refer to as the discrepancy in total emissions between two inventory estimates. So I've previous title for this talk was the switches and dials of methane reconciliation. I was originally trained as a mechanical engineer, and as a result of that, I look at any complex system as a big machine with switches, dials, knobs, and gears. In any complex system, the correspondence between your inputs that you can adjust and tune and the outputs of the machine is not always clear. Like in this cartoon, when you're doing work on your car, which is a complex machine, and you're trying to diagnose why something like a squeak is happening, it's not always straightforward to figure out why that is. You have to test and adjust multiple things. Computer models like measurement-informed inventories are no different. There are many functions involved and sensitivities that will affect what your outputs are. Goal of this remainder of this talk is to talk about what some of these functions and sensitivities are. So the way this is going to work is I'm going to we've taken some data. This is anonymized and aggregated data from Highwood Partners. We'll run this data through our MII prototypes, adjusting, for this presentation, 3 separate switches and dials, and then assessing the sensitivity of the model in terms of 3 specific outcomes. First one, the size of the pie, total emissions. Second one, confidence in the size of the pie, the uncertainty bars. And then third, how the pie is sliced. So the source category breakdown, how that total emissions estimate is broken down into different categories like equipment leaks, process vents, flaring, for example. The first experiment that we have is on source category mapping. What do we mean by source category mapping? Source category mapping is the process of reclassifying your bottom up and top down inventory source categories to a common schema for reconciliation. The measurement informed inventory process brings together your bottom up and top down inventories and compares and combines them via reconciliation, because reconciliation is the comparison and the combination of different inventory estimates. Because our ultimate goal is to make sure our bottom up estimates are matching our top down, we're investigating why, it is critical that we are comparing like for like. And source category mapping is this process of ensuring that we are comparing like for like. Seems like an obvious process, but the devil here is in the details. So on this slide, what I've done is I've taken this anonymized data and just thrown it into a bar plot. So this is what it looks like with no source category mapping. The x-axis is the various labels that exist in either the top-down or the bottom-up data. Top-down's in blue, bottom-up is in orange. No groupings yet. Y-axis is total emissions, according to either the top-down or the bottom-up, following data processing. You can see there's a lot of stuff here that should probably be grouped together in some categories that are unclear. We see various combustion emissions, compressor categories, fugitive emissions, suspicious looking groups like other sources, and then key issues, just to sort of what are some problems that typically occur in this source category mapping process? Why are there differences? There's granularity differences. The bottom-up inventory will almost always be more specific based upon its construction. There's what I refer to as the what versus the how. Top-down vendors will see a piece of equipment, like a dehydrator. Bottom-up inventories, based upon they're constructed with engineering equations, simulations, they're simulating a how, whether that be accidental leak or a purposeful vent that is happening because of a specific operations process. And then finally, technology attribution abilities, for example. Most top-down vendors will not see a pneumatic vent. So I'll highlight 2 specific cases of following source category mapping and decisions that you need to make during source category mapping. So I've taken the data shown on the previous slide, and I'll look at 2 specific groups of source categories. And for each of these examples, I'll identify 2 grouping options and the total degree of variance that remains to be reconciled with each of these groupings. So in each of these figures, The y-axis is total annualized emissions following temporal extrapolation and all the MII processes. And then on the x-axis, we're comparing top-down and bottom-up. In case one, we're looking at compressors and engines. Here, as we can see, the bottom-up inventory is capable of resolving the different types of compressor emissions, as well as the methane slip from the compressor driver, or the stationary combustion. The difference between the grouping option on the left and the grouping option on the right is, do you include methane slip from combustion in your comparison? In other words, is it appropriate to aggregate all of these emissions together in your comparison to what is seen from the top-down technology? Is the top-down technology seeing this methane slip? Not necessarily a straightforward question. And the decision of whether or not to include that, or whether or not to include that in the comparison, carries with it a variance swing of over 1,000 metric tons of methane in this specific example. The second example relates to the source categories fugitive and other sources. The reason this is a challenge is because after you grouped, you performed your source category mapping and your reconciliation for most of the, well, relatively easier to aggregate and compare source categories, you're kind of left over with these other buckets. And in this case, it's fugitive and other sources. These are both basically miscellaneous catch-all groups. Should they be grouped together? Is that an appropriate comparison? The difference in this case carries with it a variance swing of over 2,500 metric tons of methane. The obvious answer of what to do in these situations is to go deeper, investigate the data, understand what is actually contained within each of these groupings. But I figured this was worth highlighting because it has been specifically called out in UNEP OGMP public reports in terms of inappropriate reconciliation comparisons. And so looking at the outcomes that we were interested in investigating in these experiments, this has a substantial impact on the source breakdown, or the relative materiality of your final measurement-informed inventory. Second experiment relates to source subcategory grouping. So what is that? Source subcategory grouping relates to the stratified sampling approach. Before we sample, we group our population into different strata and then conduct our sampling within each of these strata. Because you can't measure everything all the time, so you have to make a decision about where you're going to conduct your sampling. And the purpose of sampling strategies like this, stratified sampling, is to ensure you don't take a really bad or a biased sample. So you group your population into different strata in such a way that you believe captures the majority of the variability within the population. So if you were doing this for your L4 or your source level inventory, you would be conducting this sampling within specific strata in order to create more finely resolved emission factors that would be used to extrapolate to the rest of the population and come up with your final total emissions estimate. So the issue here is that device populations can be grouped in a variety of different ways. And in order to perform different groupings, you need to have those labels available within your data set. So the most appropriate grouping may not be captured or labeled properly in your data set. So what is the sensitivity of the final result to these different kinds of groupings? So that's what we tested in this experiment. So here we're investigating two different possible ways of stratifying a data set. This example is based upon source level stack test data for methane slip. So this is for compressor drivers. So we've got a stack test data set, and it can be grouped by in two possible different ways. First, based upon the manufacturer of the engine, and second, based upon the horsepower class of the engine. So in these plots, again, the y-axis is the total annualized emissions. And then the blue is our top-down estimate. Our top-down estimate isn't varying in this example. In orange is the bottom-up estimate, and this is our total or bottom-up or source level estimate after the data has been grouped, the emission factors have been calculated, and the extrapolation has been performed. So comparing that final bottom-up estimate based upon these two different grouping options, we can see that there is a substantial difference in both the final total emissions estimate for each of these, as well as the uncertainty. The total emissions estimate nearly doubles when you go to grouping by horsepower class, and the uncertainty is also quite impacted based upon this particular calculation. And that's because in the horsepower grouping, this particular grouping of the data was not as effective in capturing all of the variability within the stack test data, hence the higher uncertainty estimate. Now, not only that, but depending on how you perform your groupings here, also affects if this particular source category is reconciled or not reconciled, because you can see in the horsepower grouping, this particular decision in how you're handling the data leads to a reconciled inventory. So to summarize, this particular sensitivity in the analysis process leads to a substantial impact on both the total emissions estimate as well as the final uncertainty outcome. So the final experiment is relates to top-down sample size. So from a top-down perspective, the sampling question comes down to how many sites do I sample and how frequently do I sample? This figure is from the OGMP reconciliation and uncertainty technical guidance document. In this guidance, it's discussed how sampling is based upon the materiality of the source category, so how important that source category is from an emissions perspective, the complexity of the sites, the population size, and it's also recommended to consider the variability of your population's emissions distribution. This is critical because research by a variety of labs has shown that the skewness or the variability of your emissions distribution has a substantial impact on the required sample size to achieve an emissions estimate that with reasonable confidence. Couple issues is that early in an operator's emissions journey, the expected emissions distribution, to use Veritas language, is not always clear. You may have not conducted top-down sampling yet. You may not have enough data to construct an expected emissions distribution. And then for many operators, frequent site level measurements might be infeasible, but it also might be driven by other priorities besides gathering an effective sample size, for example, to meet LDAR regulations. So irregardless, how important is this from an MII perspective in terms of sample size collection? So that was the objective of experiment 3. So what we did is we took a set of aerial top-down data, and what we did is we simulated what if the operator only performed 1 survey, 2 survey, or 3 surveys. So within this data set, it was 4 surveys conducted over the course of the year. So we sort of will say, for the purposes of this experiment, that the true annual emissions are those based upon the 4 surveys. So calculate the annualized emissions based upon the 4 surveys, and then compare compare total annualized emissions as if there was only 1 survey per year, 2 surveys per year, or 3 surveys per year, and then calculate the mean error in terms of bias and random variability from our true estimate. So what does that look like? So on this plot, on the x-axis is the different points to the different subsets of data that were used for this calculation. So total annualized emissions with survey 1 only, survey 2 only, or survey 1 plus 2, survey 1 plus 3, et cetera, et cetera. And then on the y-axis is the difference from the mean difference from the true emissions. And looking at the different sets of 1 campaign only versus 2 campaigns only versus 3 campaigns only, compared to our true estimate or the 4 campaign average, we see that with 1 campaign only, it's on average a 17% bias with 53% variability. With 2 campaigns only, it's less bias, 6% bias and 57% variability. And then with 3 campaigns only, it is 2% bias and 22% variability relative to our 4 campaign average. So clearly this has an impact on both your total emissions estimate and as well as the uncertainty or size of your error bars. So this was just a set of 3 experiments that we've conducted with our clients. There's many more. This is just another selection of other switches and dials that exist within the measurement-informed inventory process. What types of uncertainty should we be including in our final comparison? How do we apply quantification uncertainty from measurement technologies, given that we're still working on standardizing this process? Should we be applying bias corrections? How to infer the magnitude of below MDL emissions? These are all other switches and dials that we haven't touched here. So just before we go to questions, a brief note about what work we're doing at Highwood from a software perspective. So we're performing these experiments through our emissions intelligence steering committee. This is a group of progressive operators that teamed up with us back in 2023 with the goal of systematizing MII calculations. We've done a lot of work like this where they share with us their data. We run it using different types of MII calculations, some based upon our own design, some based upon work in the academic literature. And the goal is to automate some of this complexity while also preserving the rigor. And then what we did is we turned that work into software, which was launched in January of this year. It's called the Emissions Intelligence Platform. We like to think of EIP as TurboTax for measurement-informed inventories. I think it's a good analogy. Tax regulation is vast, but nobody expects mortals to memorize or understand it. However, the IRS, CRA doesn't compromise on rigor. There's still a need to get it right. So we take care of the hard stuff in the software, data pre-processing, guidance for source category mapping, which I showed here, sampling guidance, emission factor generation, emissions annualization, et cetera. So our software customers obviously include operators that are seeking an efficient way to reach OGMP 2.0 gold standard, but it also includes clients who aren't signatories to OGMP, but are simply using measurement-informed inventories to improve internal clarity and understanding of their emissions. So a few final thoughts. One thing we talk about a lot in this space is the need for harmonization or standardization of measurement-informed inventories. What we found is that this standardization requires a certain level of rigor to simply guardrail all the different assumptions that are inherent to the process. So lacking those guardrails, we will not have harmonized or comparable measurement-informed inventories. So work we've been doing at Highwood, our goal is to find a balance there somewhere in the middle that'll get us, get us to a place where measurement-informed inventories can be scaled up and operationalized by operators, while also at the same time preserving the necessary complexity of this process. So thank you very much for listening, and it looks like we still have quite a bit of time for questions.